Have you ever just stopped and wondered what actually happens in that split second after you type something in a search box and hit enter? I mean, it feels like pure magic, right? But behind the curtain, search engines are fighting these two colossal battles. First, how do you organize an ocean of information that's getting bigger every second? And second, how do you do all that without, boiling the actual oceans? It's this incredible balancing act, and it's at the very heart of how modern search works. So let's break it down. So just to give you an idea of the scale we're talking about, look at this number, 1.2 billion. That's how many documents were in a single research web collection, and that was way back in 2009. The internet today is it's unimaginably larger. So the first challenge is just that. How do you even begin to get your arms around this astronomical amount of data? And that's where the second, maybe less obvious challenge comes in, the cost. Every single search we do, as tiny and insignificant as it seems, has an environmental footprint. Now, this specific number is a few years old, but the idea behind it is more important than ever. All our queries added up consume a massive amount of energy. So the twin challenges are crystal clear. How do we manage basically infinite information using very finite resources? All right, so let's tackle that first problem, organization. Before a search engine can find anything for you, it has to create a map of the internet. And the process of drawing that map, that's called indexing. The absolute key concept that makes search possible is something called the inverted index. So instead of listing a document and then all the words inside it, it does the exact opposite. It lists every single word you can think of and then points to every single document where that word appears. It's just like the index at the back of a textbook telling you exactly what page to turn to. It's the master map. Now, the old school way of building this giant index was pretty logical, but it was also really limited. You'd have a single computer, right? And it would just chug along, reading documents one by one, creating these lists of words in its memory. And when that memory got full, it would just flush or dump that partial index onto the hard drive. Then it would start over, and at the very end, it would try to merge all those little pieces into one giant master index. And you can probably see the huge bottleneck right there. The web just got too big, way too big. No single computer, no matter how beefy, could ever hope to build an index for billions of pages. The system was just destined to grind to a halt. It simply couldn't scale. So this is where Google had a breakthrough that really changed the game. Instead of trying to build a single, bigger, faster computer, they asked a different question. What if we used thousands of regular commodity computers all working together? And this led to this incredibly elegant approach called MapReduce. So the first step is called map. Imagine you have a 10,000-page book to index, an impossible job for one person. So you rip the book into 1,000 chapters and give one chapter to each of 1,000 different librarians. The map function does exactly that. It takes the massive job of indexing the web, breaks it into millions of tiny, manageable pieces, and sends each piece to a different computer in a huge cluster. The second step is reduce. So once each of your 1,000 librarians has finished indexing their chapter, a head librarian, that's the reduce function, comes along and collects all of their work. It carefully sorts and merges all those small, partial indexes into one final, comprehensive master index for the entire book. So you can see the night and day difference in this approach. The old way was monolithic, it was brittle. If that one machine failed, you lost everything and had to start over. It was a nightmare. But the MapReduce way, it's distributed and it's resilient. You have thousands of small tasks running at the same time. And if one computer fails, who cares? The system just shrugs and calmly hands its little piece of the job to another machine. This innovation is what allowed search to finally conquer that challenge of scale. Okay, so MapReduce solved the problem of finding all the documents that have your search terms. But that just creates a brand new problem, right? How do you sort through potentially millions of results to show the most relevant ones at the top and do it efficiently? Well, modern search engines use a multi-stage pipeline. Think of stage 1 as a bouncer at a club. It uses a fast, pretty simple algorithm to quickly look at millions of pages and let just a few hundred of the most promising ones through. Then, and only them, those few hundred candidates get passed to the later stages, where these incredibly powerful and complex AI models do the final, precise ranking. But here's the catch. Those powerful models are total energy hogs. So the better the results get, the higher the computational and, environmental cost. So what if you could make that first stage, the bouncer, smarter? If we could give it a better initial list of candidates, then the heavy-duty AI models down the line would have a lot less work to do, saving tons of energy. This is the whole idea behind using what are called priors. A document prior is basically a pre-calculated score that gives a document a little head start in the ranking race. It's a static value, assigned when the document is first indexed, that reflects some kind of inherent quality or importance, and it's completely independent of any specific search you might do later. Now here's a really fascinating idea from some recent research. What if a document that uses a lot of words that are also common across many other documents is in some general sense more central or important? We're not talking about rare keywords here, but about sharing a common, foundational vocabulary with the rest of the web. So how does this total document frequency prior actually work? It's surprisingly simple. For every word, we count how many documents it appears in across the whole collection. Words like science, which show up in lots of documents, get a high score. Then, for any given document, we just add up the scores of all the words inside it. And as you can see here, documents that share more common, foundational vocabulary, like the first two, get a higher initial score. It gives them a little boost right out of the gate. And the big question is, does it work? Oh yeah, absolutely. This chart shows the results pretty clearly. The bar on the left is a standard ranking method, kind of the baseline. The bar on the right is that same method, but with our smart prior added in. That big jump in height shows a significant improvement in how relevant the search results are. This means the expensive, energy-hungry later stages get a much cleaner, more relevant list to start with, which saves a huge amount of work.
So what does all this tell us about where search is headed? Let's bring it all together.
We started with two core challenges. The scale challenge, indexing a constantly exploding internet, was met with the innovation of MapReduce, that awesome divide and conquer strategy. Then, the efficiency challenge, getting great results without huge energy costs, is being tackled by innovations like these smart priors, which make the whole process smarter from the very first step. And this really is the key takeaway. The future of search isn't just about more brute force, about being bigger and more powerful. It's about being smarter, more efficient, and ultimately more sustainable. And that leaves us with a final question to chew on. As we build these ever more powerful AI systems, maybe the most important innovation won't be about raw power at all. Maybe it's about finding these elegant, efficient solutions that let us do more with less. What do you think?